Hey guys, this is the Physics 2 post-quiz tutorial, and today we're going to be doing Chapter 15, Problem 71. So let's get started. Here we can see the problem. The problem states that a thin, hollow, spherical plastic shell of radius r, shown here, carries a charge of negative q. To the left of the spherical shell are four charges, packed closely together. The distance from the center of the four charges to the sphere is L, which is much larger than S, which is the separation distance between the charges. So let's look at this problem. We have the sphere here with a uniform charge, negative Q. Then L away, we have the four charges that we can split actually into two crossing dipoles. We have our horizontal dipole here, and our vertical dipole here. And later we're going to be able to use the simplified dipole equations because S, the separation distance, is much less than L, our distance to the sphere. For our problems, we're also going to have to know location B, which is distance B away from the right side of the sphere, on the opposite side from our charges. Let's go to Part A. Part A asks us three things. It asks us to calculate the x component of the net electric field at B, the y component of the net electric field at B, and to show the electric field on the dipole. Let's start with the x component. The x component is going to be defined by the sphere and by the horizontal dipole. That's it. So know that E net x is equal to the electric field of the sphere plus the electric field of the horizontal dipole. Now, let's start with the dipole. We can use the dipole on-axis equation, making things easier. We know that E of the horizontal dipole is equal to 1 over 4 pi epsilon naught times 2 times the charge times the separation distance divided by the radius cubed. Now we put our own values in there. We get that it's equal to 1 over 4 pi epsilon naught times 2 qs over L, the distance from the center of the dipole to the sphere, plus r, the radius of the sphere, plus b, the distance to our point, all cubed. Now let's get to our sphere. Our sphere is interesting because when something is outside of the sphere, we can take the electric field of the sphere as a dipole from the center of the sphere. That means that the electric field of the sphere is going to simply be 1 over 4 pi epsilon naught times the charge divided by the radius squared. Now with our values, we get that the electric field of the sphere is equal to 1 over 4 pi epsilon naught times negative q, remember we have a negative charge, divided by the radius of the sphere plus the distance to our point squared. Thus, when we throw all of these together, we get E in the x direction is equal to 1 over 4 pi epsilon naught times 2qs divided by L plus R plus B cubed minus 1 over 4 pi epsilon naught times q over R plus B squared. Remember this minus sign, very important. Let's get to calculating the y component at B. Now the y component is going to be much easier because it's only going to be defined by the vertical dipole. Thus, E net in the y direction is going to equal the electric field of the vertical dipole. We can again use one of the simplified dipole equations, but this time we're going to be using the perpendicular equation. Thus, E in the vertical direction is going to equal 1 over 4 pi epsilon naught times the charge times the separation distance divided by the radius cubed. Now the difference is between this and the on-axis is there was a 2 here, now there's not. That's important to remember. Just qs. Put in our own values, we get that E in the vertical direction is equal to 1 over 4 pi epsilon naught times qs divided by L plus R plus B cubed. That's it. Now our final part is going to be show this on our diagram, and here it is. We get that E of the sphere pointing back towards our charges. E of the dipole from the positive side is pointing out, and E of the vertical dipole, positive side, pointing up. Simple enough. Let's get to Part B. Part B asks what assumptions were made in Part A. Well, we're not looking at the x components of the vertical dipole nor the y components of the horizontal dipole and sphere. That's because these fields, they're mostly negligible or canceled out. Now we get to Part C. Part C actually changes the problem. Part C states that the plastic shell is now removed and is replaced by an uncharged metal ball. At location A, inside of the metal ball, a distance B from the outer edge, draw and label the electric field E ball due to the ball charges and E field. E4, we're going to state it, which is the electric field of the 4 charges, and explain. Well, we have our answer here. As we saw, we had the electric field of the dipole pointing up, pointing out. Thus, this side is going to be positively charged. Because this side is positively charged and it's a metal ball, the negative charges are going to be coming to the bottom left side. Thus, the electric field of the sphere is going to be pointing down, and as we stated, we already know the electric field of E4, which is pointing up. And if we state that, E4, we saw they pointed up and out, thus E4 is pointing in the angle direction. The electric field of the sphere is pointing down towards these negative charges that are going to be here. That's actually what part D asks us, which is what is the distribution of the ball charges. Here we can see it. Positive up here, this is where our E4 was going, and negative where our electric field of the sphere was going. The final part asks us to calculate the X and Y component of the net electric field at location A. Now I know that you're thinking, oh man, we're going to have to do a lot more math. That top part really got me, confused or whatnot. Don't worry, this is very simple. Because it's inside a conducting sphere, which means no matter where you are, your charge is going to be canceled out. That's right, the net electric field anywhere inside a conducting sphere is 0. Thus, the X component of the electric field is 0, and the Y component of the electric field is 0. Thank you very much for watching. Have a good year.